Hi, my name is Nathan Ike from Aerial Services, and I want to talk about where do UAS stack up versus manned aircraft in remote sensing. I want to talk in general about three geospatial products. In my opinion, the most common is orthoimagery, basically a flat 2D composite or mosaic of images taken from above, and those are usually assembled into one giant orthomosaic. I also want to talk about elevation or 3D modeling, typically of the ground for engineering purposes, but also maybe of structures or power lines. And finally, I want to wrap it up talking about mapping, which is vectorizing geospatial data in 2 or 3D. That mapping is sometimes a combination of orthoimagery and elevation and 3D modeling. So the first part, orthoimagery. That's the process of taking airborne pixels and projecting them in the right place on the ground. You need three things for that to happen. So you need the airborne location and orientation, or the EO, external orientation, to determine the location of the sensor. You also need calibration information for the lens and sensor so that the pixels within an image, that's a 2D unprocessed image, can be projected to a spot on the ground with a given angle. And you need the surface to determine the location on the ground to figure out exactly where that angular pixel projects itself to on the ground. So that way your geospatial products, or that way your orthoimagery, is geospatially correct. Spatial resolution is generally given in terms of GSD. For satellites, that's on the order of 1 meter, or 1 meter per pixel. For manned fixed-wing aircraft, that's generally in the range of 5 centimeters and above, and you can't usually go much lower than that due to the speed of the aircraft. For manned helicopters, because the helicopters can fly a lot slower than fixed wings, you can get GSDs in the 5 millimeter and above range. UAS, which are some of the slowest flying aircraft, can fly lower and slower and collect down to the 1 millimeter GSD range. Capacities of these systems for orthoimagery are generally sun angle based. You have to be collecting during daylight hours in order to take orthoimagery. The technology to do that at night doesn't exist currently. In the manned systems, the capacity is based on the flight time in the aircraft, and typically the flight planning parameters include a 20 to 30% side overlap due to very accurate EO and IO. Those are your external orientations and your internal orientations or calibrated sensors. And you have existing or a LiDAR surface included with that, so you can fly at much lower side overlaps. We typically fly manned aircraft frame-based systems at 60% front overlap for redundancy and the ability to autocorrelate or generate a better surface than the existing DEM. We could fly as low as 20%, but because it's not any extra flight time, we typically fly at 60%. We also have beyond 350 megapixel sensors, so there's fewer frames and less computational power needed to process versus UAS. One 350 megapixel frame is easier to process than 10 overlapping 35 megapixel frames. We don't need any additional overlap to build a 3D surface to orthorectify the imagery like unmanned systems do. Altitude is unrestricted, so downsampling isn't needed. We don't have a 400-foot ceiling. We can typically fly as high as we need, just depending upon our aircraft. And that lets us be more efficient. In general, orthoimagery is not a true ortho, so rooftops or buildings may lean. In order to make a true ortho, it takes a lot more work, and it takes a much more involved DEM in order to make sure that the rooftops or the buildings do not lean. Manned aircraft sensor introduced fewer seam lines, both with frame-based and push-broom sensors. Manned aircraft are, however, GSD limited. And that's when we get into the argument of manned versus helicopters. Helicopters fly slower, and they can also fly lower legally. So that allows them to collect data at a much higher resolution, although it takes longer and is much more expensive. Let's talk about some of the details of the capacity of unmanned systems. Unmanned systems are typically flown at 60 to 75% side overlap to self-calibrate the sensor on every project. 75% front overlap is very common for 3D surface reconstruction. UAS are line of sight limited and forward speed limited for a variety of reasons. Those reasons include blur because the sensor does not have forward motion compensation, rolling shutter distortion that affects both the EO and the IO, Altitude and field of view also limit UAS, and sometimes speed does as well. 15 centimeters is generally the GSD for multispectral sensors, all the way down to 1 centimeters for fixed-wing aircraft. Below 1 centimeter GSD generally requires a multicopter or a hovering aircraft of some sort. Unmanned aircraft also requires AT or aero triangulation and significant processing time, often more than collection time. To increase the capacity of unmanned aircraft systems, a few different pieces of technology can help. IMU and GNSS tightly coupled solutions that are post-processed can help reduce the amount of side overlap necessary. Calibrated stable cameras with leaf and mechanical shutters also help increase the stability of models and accuracy. Cleaned DEMS without above-ground features reduce the number of artifacts in UAS imagery as well. I'm Nathan Ike, Geospatial Products Manager at Aerial Services.